Okay, let's get started. This is the last talk of the symposium. We have Dr. Derek Johnson from A123 System. He gave us some industrial and technical perspective based on some fundamental understanding of the carrying system. So Dr. Johnson is a vice president in global R&D of this A123 Systems. He has global responsibilities focused on developing, implementing, and executing the battery's high power and high energy technology development roadmaps. And before he joins A123, Derek was the vice president of operations and technology development in Create the Battery, a company he co-founded based off core technology that he had developed in Professor Creato's academic laboratory during his postdoctoral fellowship. And also in Creato, he interacted with key strategic partners throughout the lithium-ion value chain to identify key market entry points for the company's proposed products and also many beneficial joint development projects. He has extensive experience in 3D electrodes and electrochemical energy storage devices, and also he sits in Symbiosis Technologies Board of Directors, for which he is inventor of its core technology. With that, let's welcome Dr. Johnson.
So first, I'd like to thank Young and the organizing committee for inviting me here. Today it's been a great day, a lot of really good talks, and I know I'm the last speaker, so thank everybody. Thank you to everybody for staying. And so really, what I'm going to focus my talk on is really a material development approach in the deployment of that technology to solve some fundamental problems for high-powered systems, which we deploy for start-stop and mild hybrid electric vehicles, which is based off of LFP chemistry. And then also our work that we're doing in the high energy density automotive applications, which I split it up into two different areas. One is the NMC, or the layered oxide, and then also some work that we're doing in the solid state realm. But the key is still really the theme of the day. We're taking a fundamental approach at the materials level to try to solve a problem, whether it's inherent in the technology or it's a customer requirement. So the way I'm going to break the talk up today is the company overview. I figured there would be a lot of students here today, so I will take the opportunity to pitch A123. We've grown quite a bit, and actually, if you like high-paced environment, collaborative environment, the ability to travel, we'll talk about that as the fundamental R&D department within globally. A123 has grown quite a bit, and then split it up into LFP, the high nickel NMC. So really focused mostly on 80% nickel or higher, but there is a little bit of information on 622, and then some of the interesting results that we have in terms of the solid state battery development that we're doing in house. So we have all of these other things that go on: global headquarters, electrode cell manufacturing systems, sales, engineering. But really just want to focus on the research and development. So I've been with A123 for over 4 years now. And there's quite a number of locations. So I have 4 teams globally. The first one is based outside of Boston. It's the biggest. When I first started 4 years ago, there was 13 of us, and now there's over 76. So there's been a really big commitment, mostly PhDs, with the appropriate amount of engineers and technicians in the laboratory. That's where the global directive comes from, and we work on everything from solid state, silicon anode, liquid electrolytes, both for low voltage and high voltage and fast charge application. There's also a team in China. Again, when I first started, it was 10, and we're building it up to 65. We'll finish that by the end of this year. There is also a team that really focuses on the LFP powder development. That's in Michigan. This is really important key part of the business, because based off of our development in low voltage, which is really a function of the increased performance of the LFP, over the last 2 years, we booked per year over $1.4 billion worth of business in low voltage. So there's a big growth there. And then I think it was Jean-Marie who had mentioned the Innovate UK, the Faraday program. So we actually partnered with McLaren and applied for that grant, and we won it. And so we're working with McLaren. And so right now I've just kicked off, and we're building a team at Warwick University, that's right outside of Coventry, in the UK. And this is really exciting, because the goal in about 14 months from now is to provide McLaren with about 750 50 amp hour solid state cells, so that we could build into a pack and put it in a vehicle, just to validate the concept. It's not going to be 400 or 500 watt hours per kilogram, or not anywhere close to that, but to actually demonstrate that this sort of technology in managing some of the rate performance or the low temperature performance issues can be mitigated at the pack level. So there's a lot of very fascinating things going on at A123 right now. Just to remind everybody, we're essentially 18 years old now at A123. We were founded really as a material science company out of MIT. Again, the core tech is LFP. This has continued. We've been through a number of generations. I will talk about the latest generation now for ultraphosphate, which has really enabled our business in low voltage, and the reason why we're winning a lot of business. In 2014, we really also started focusing on oxide cells as well. So these are really the two key focuses. LFP first started with 111 in 2014. We actually launched our first global 111 cell in 2016, and then at the end of last year, we launched our first 622 cell EV, and that was for Chery. And I think it was Mark that had mentioned it earlier. Really, the biggest market for PHEVs and EVs is actually in China right now. And what's actually fascinating is a lot of our business for low voltage is split between Europe, and China, and I'll explain why that's the case. So that's the company overview. So hopefully I've given the impression that it's exciting. There's a lot of work, and we're hiring. So if you're motivated and you want to be part of a dynamic team, then let me know. So LFP. So why are we interested in this, especially for the start-stop applications and the mild hybrid electric vehicles? This is really the only system that we have on the market right now that actually you get pull from the automotive companies. Okay, we can actually make money off of this. Our margins are about 12 to 20% depending on who we sell to, and we don't need any subsidies from the government. And so, so this is a low-cost approach for the automotive makers to reach between 3 to 4, all the way up to 15% fuel economy savings. So depending on your fleet vehicles, you can incorporate a system that maybe costs an additional couple $100 to maybe something that costs an additional $500 or $600, and still realize some of these savings. That, in comparison to what you would need for a PHEV or an EV pack, which is now into the thousands or tens of thousands of dollars, it really allows the end users to have a diversified approach to solving this particular issue. And again, with the technology that we bring to the table, we're the only LFP company that sells into this particular space. We can actually make money, which is important, because for the EV market to really take off, we've got to get to cost points where we're not going to require government subsidies to make this happen. So we did pretty well for a while. Essentially, our Gen 2 12-volt lithium-ion starter battery had decent volumes. And we were really supplying to the higher end European automakers, just to support some electronics. The problem is that when you look at our initial LFP, which is this was actually our Generation 3, and this is our Gen 4 LFP, which was trademarked as nanophosphate. What you're really looking at are cold crank pulse. So it's the power as a function of time, and you're looking at different pulses. And then I have two different curves here: the beginning of life, and then at the end of life. And so for our older version of the technology, this was pretty good. But if you actually compared it to the actual lead acid AGM battery, you could see even at 18 degrees C, we couldn't supply the cold cranking amps that are required. So AGM not only had a cost benefit, right? It's only about $70 to $80 per kilowatt hour, but it also had a performance benefit. And that performance benefit is further increased when you go to about negative 30 degrees C, which, believe it or not, is required in certain parts of the world. The performance, dramatically decreases. I was born and raised in Miami, so we never saw minus 30 C. So anyway, this was good, but again, really, it was the total cost of ownership that was driving some of these high-end vehicles. So we continue to push, and this is LFP advancements completely done internally at A123. And now you could see the power increase was incredible, and these are R&D cells. Not only at the beginning of life, but our end of life performance is actually still considerably better than beginning of life in the previous version. So now what you do, if you then create our Gen 3 60 amp hour battery, which is directly comparable to a lead acid AGM, we blow the competition away in terms of cold cranking amps at minus 18, and we're actually even better at minus 30 now. And I'll talk at a high level of what we did to make this happen. So what this has really done is it's taken away the performance barrier to launching lead acid, lithium-ion for 12-volt applications, but also to incorporate into 48-volt systems to get higher fuel economy. So what did we really do? So we went back all the way to the beginning and looked at actually the morphology and the structure of the precursors. So the development strategy on going from the nanophosphate, which the last version of that was our Gen 3.5, all the way to our first version of our ultraphosphate, our Gen 4, is we looked at the solvents that we did for our slurries, because that had an impact on the morphology, both on the primary and secondary particle structure. The precursors are key. A lot of people don't really pay attention to this, but in this particular case, the two key ones were the dopant precursor and also the iron phosphate. Looking at the BET surface area, the density, how that interact, how that could be milled to get all the components together, but also more importantly, how those precursors actually decompose during the thermal reaction to get the final product, so that you can actually control the speciation on the surface of the material. So again, I kind of highlighted all that together in terms of solvent for the slurry, precursors, doping, surface morphology, the speciation on the surface. All of this is really, really important. And so you could see from some high-level SEMs, we go from something that looks like this to something that's very compact, very spherical, and very controlled, all the way down to the primary particle. And so really, we had our irregular particle shapes, smaller particle size. The cap density was not very good, and the impedance was low. But now we could go to very dense spherical particles. This is very important for processing. Even smaller particle size at the primary LA, because this is a first order phase transition, so you want the characteristics lengths to be as short as possible, and then this resulted in much lower impedance. So really, the key point to this is that we're really passionate about our R&D, and we're really focused on developing this internally and transferring this to production. So oh God, that's a great question. So, oops, let me go backwards. I could tell you it's probably on the order. So this guy right here, I would say, is probably about 8 microns. So the primary particle size, it varies between 60 and 80 nanometers, and our D50 typically is around 3 to 4 microns. Yeah, that would have been helpful to have a scale bar on this. My apologies for that. And so we started this all the way from the benchtop, where we would make a few grams, and actually this year we transferred this to our strategic manufacturer, and we're going to make 2,000 metric tons this year to supply this particular product. And so what this has really done is this is kind of the beginning of the journey, right? And so we have our core products here. What we're looking at is the usable energy for 48-volt microhybrid systems versus the peak power. So our first version of this has actually satisfied the market pretty well. So what you're looking at are the end user requirements and what we actually have out on the market right now. But as you're seeing, to be able to support more propulsion, to be able to support higher end electronics, you're seeing that the power requirements, or the peak power, is not degrading. It's actually getting higher, and then also the usable energy is getting higher as well. And so what we're doing is, again, taking a fundamental approach to look at things like DCR growth to minimize that, looking at making higher thermal stability so you don't get calendar fade, so that at the end of life you really have very similar to performance at beginning of life, so that we can meet these higher energy density values without degrading power. So again, this is kind of the first step in our journey with our Gen 4. And this has gained us about 50%. We have about 50% of the market in Europe and in China with this product. Because of this, we actually won the PACE Award. Again, really proud of my team for this, because this is all enabled by internal development. Only LFP solution for this, which is big because it's cobalt free, right? So we're not, the commodity price for cobalt has been up and down over the past 3 or 4 years, and this is not impacting the price of our product. So this really gives us a lot of supply chain security. Also, because the power is so good, we don't need any active cooling. There are NMC or oxide solutions for this, but that requires active cooling. And this is really safe. Even though this is very high power, we do these sort of nail penetration tests and stuff like that you showed, and there's no flame. That's one of the big advantage of going with this olivine type of structure. So that's what we've done on the LFP side. A123 is known for that, but to really compete in PHEV and in EV applications, we have to have an oxide solution as well. As Stan mentioned, this was really driven in China because of the subsidies. It's really interesting, because in the past 6 to 8 months, SAIC, they've all come back and said, oh my God, we're losing the subsidies. You need to come up with an LFP solution now for PHEV applications because of cost, right? So we're seeing this oscillation, but if, from my perspective, I look at, R&D as kind of the aircraft carrier, so we can't make these quick sort of turns. So we're still really focusing on the future to come up with a high nickel solution. And what we're really focused on is not continuously to increase the capacity that we're actually getting out of the powder. What we're really focused on is following that trend, but imparting this sort of cycle life and thermal stability that's really required, so that we have a superior abuse tolerance. So what's the motivation? So when we really started launching our global oxide cells, this is our particular performance. I took everybody's name off because this was for an internal documentations, but these were our competitors, and then these are the Chinese MIIT targets. So really, what was clear to us, and not really a surprise, is that we were behind the Koreans, the Japanese, and the French. I mean, there was no denying it, and we were going to be there for quite a while. So we had proposal for some significant influx in funds and resources for R&D to try to change this path to catch up with the LGs and the Samsung SDIs and the Panasonics of the world by 2018, 2019. This has proved fruitful. We've made this progress. This is a little bit better than really what it is. So I would say we're not quite there, even though this is showing we should catch up by 2019, but we've definitely made some progress. The other issue is, and I have a nice illustration for the solid state, is that as we start to climb this energy density ladder, being able to keep the cell safe and at the cell and at the module level becomes increasingly difficult. And so this is a cell that was underwent an overcharge test that had some abuse tolerant technologies that we included, and this is what happened and this is only a 3-cell module, and this is what happened when it didn't include it. And this was only at, I think, 260 watt-hours per kilogram. So for us, we really want to continue to climb this energy density ladder, but we want to do it in a safe way. I mean, we've seen it, right? The Tesla overcharge scenario in Shanghai. You don't see it very often, but Geely is moving towards 811, SAIC is, and there are prototype cars that are on the street in China now that are spontaneously catching fire because at the pack level you need some additional safety measures, because the 80% nickel and greater has more difficulty at providing the sort of safety that the other chemistries don't. So to try to import that, we've taken the same approach as we've done for LFP, where we want to modify the actual crystal structure, and in this case it's through surface optimization or doping, where we're increasing the bonding strength between the transition metals and the oxides. Also putting some dopants, if they have the right ionic radius in the actual lithium layers to act as pillars, so you don't have that C direction collapse when it's under abuse conditions. And so we've partnered with Argonne. We've been partnering with them for almost 3 years now, and there's this really nice strategic relationship where we do synthesis and development at the R&D laboratory scale. Argonne does it as well. We compare notes and make improvements there, while at the same time have pilot scale facilities in the R&D group at Hangzhou, China. So anything that's interesting that we've learned from a coating or a doping standpoint, we can transfer to the pilot line, because that's very, very important to see if it's actually transferable to manufacturing, and then we scale up from there. I'm going to go a little bit faster because I want to get to the solid state aspect of this. And so, as you can see, as I've mentioned before, what we're really looking at is two things. One in the bulk, which is the cracking. And so we've come up with some interesting doping methodologies and elements that actually help reduce this cracking by relieving the stress during cycling. And this actually helps with from an abuse standpoint, but it also helps in terms of the life of the structure. And then also, as John Marie talked about this quite a bit, interfaces are key in this. And so, especially when you start to get to 60, 70, and 80% nickel, you really have to control the interface of the particle, both at this primary and secondary level, because those interactions with the electrolyte can actually drive some of these reactions that either hurt the performance from an electrochemical standpoint or from an abuse standpoint. So just some initial data. We really look at DSC as well to try to gauge whether we're making some progress. So again, we've developed this in a way using the advanced photon source as well at Argonne to correlate where we start to see the C direction collapse or the formation of the rock salt structure at the surface with what we're seeing from the DSC. But then what we've done is we've taken that and built full-size cells between 50 and 60 amp hours to say, okay, if we get this response from the APS or this response from DSC, what does that translate to the cell level? Well, if this passes, will these cells, if we make some changes, like let's say to a 70% nickel, we get this same sort of response that we would get from something that would be 50% with no coating. We get the same DSC, the same APS sort of response. Do we get better abuse performance? And so this is really what this is highlighting. So in this case, we're looking at the total energy release or the shift at the onset temperature. This was for a coating for 622, and you can see when we shift this and apply the coating A, we can maintain low UCAR levels, which is 4 or below is actually passing. And again, this is kind of just what I discussed earlier in terms of utilizing the brain power and the resources at Argonne. This is typically, so this is the onset temperature. We're looking at the DSC result for 50% nickel, and we could see how we could start to look at the C lattice drop corresponding to the DSC result. We know that that this cell, when designed correctly, will pass all the abuse tolerance testing. So the key for this program was then to take the NMC at 60 and 80%. And shift all of this collapse in the DSC to something equivalent to the NMC 523, and get the same result. And this is what we've been able to do. So with a combination of coating and doping, we've made cells. We've been able to demonstrate through, again, the DSC that we've made the type of improvement that we're looking for. And so what you see here is the nail penetration result for a pristine NMC A11 cell. This failed with a UCAR5. You could see the char there, but when we use our special coating A and B, and this was done at the pilot level because we need to make enough material to actually produce the cells. I think these were 46 to 48 amp hours. You could see that we passed nail penetration. So here's the voltage trace versus temperature. What this is doing is it's really mitigating that reaction at the surface that releases heat and oxygen, so that it doesn't react with the electrolyte to essentially start a fire. So that was done with an 811 graphite. Those came in at about 260 to 270 watt-hours per kilogram. So we wanted to take the same approach but up the energy density. So the way that we did that was by incorporating silicon in it, so we can consistently be over 300 watt hours per kilogram. With silicon, we incorporate these doping and these coating efforts into these particular cells as well. And you could see these are 84 amp hours. 84 amp hour cells, again, made on production intent equipment, and you could see that it's a very benign result. Really, this UCAR3 rating means that essentially there is enough heat that's generated internally so that some electrolyte actually evaporates out of the cell, but there's really no flame or any sort of reaction. And we have been able to show this for both nail penetration, overcharge, and hot box, and we're doing this for crush testing as well. So this would be great. I wish we could take this to market now, but the issue with silicon, even if you have a great cathode, doesn't change, right? The cycle life is still not sufficient. And actually, even a bigger problem is at the beginning of life to end of life thickness of the cells. It swells so much that we have module problems as well. But again, if that's something that you have expertise in and you'd like to work on it, come talk to me after the presentation. So finally, quickly, I want to get into the solid state development. So we're taking those learnings on the cathode side, also on the anode side, and some strategic collaborations with ionic materials to really start looking at what we can do from a solid state approach. So I think, and I'm not telling you anything you don't already know. Really, the promise of solid state is higher energy density, safety. From a supply chain standpoint, we're really not seeing any reduction in cost at the cell level, but you see a huge reduction in cost at the pack level because you could pull out a lot of the mechanical rigidity, safety, BMS things that are required for traditional lithium-ion batteries. And so I like this chart to really kind of highlight what we're really seeing. So it's the UCAR rating. 2 is great. 6 is bad. That's pretty much kind of an explosion as a function of the cell energy density. So the cells that we make, so you could see from 150, that would be something like an LFP or a 111 cell going to pushing 300, which again is 80% nickel or higher. If we just use off-the-shelf materials, we can't make anything as we approach this energy density that's any lower than UCAR 6. When we start utilizing our modified cathode materials, we can drop this, and we teeter back and forth between passing and not passing. But really, with solid state, what the hope is, again, is that because we have nothing flammable, that we should be able to maintain this UCAR 2 and UCAR 3 rating as we drive towards higher energy densities. So this has been demonstrated. You'll see in just a minute. It's not impressive. It's only 200. But the key thing that I would put here is that these are actually 15 amp hour cells that we've made on production and manufacturing equipment. So that's the direction that we're going there. How we're getting there is we're actually taking a staged approach. We're doing a proof of concept with just 811 and graphite and overcoming some of the issues that is inherent with the interfacial resistances and taking this to manufacturing. So this is the proof of concept, and right now we're between 1 and number 2. The reason why, and then this is actually silicon. It doesn't look like it came out very good, but this is incorporating silicon in the anode. The reason why we're staying away from lithium, at least right now, is exactly what was discussed earlier, is that you have this additional issue in terms of dendrite formation. So what we're trying to do is get to between 300 and 350 watt hours per kilogram with traditional materials in the solid state, so that we can demonstrate that it is viable for the automotive market without having to solve everything at once and jumping right to a lithium metal anode. And we think it's paying off. And so we really started this collaboration and this push in solid state in June of 2018, and we have this schedule. And this is again builds that are done on production intent equipment. So these are 15 amp hour builds in our manufacturing size format, and you can see here's our volumetric energy density, our target, and our actual. So we're right here, and we feel very confident that by the end of this year we actually will get to 300 watt hours per kilogram. I actually just saw the data. This is our goal for the end of June, and the metrics that we are trying to hit in terms of coulombic efficiencies, we achieve them. So we should be able to hit this energy density by the end of June, and I feel confident that we'll march towards 300. This is going to be more of a risk because of the high silicon content. But the point is in a very short period of time with commercially available, active materials, at least on production equipment, we're very, very quickly reaching the 600 watt-hour, over 600 watt-hours per liter and 300 watt-hours per kilogram, utilizing solid-state chemistry. I got to take a second to try to show the video. Let me see if it'll work. So this is a nail pen video as well. This to me is really quite fascinating. So you saw it came down, oops, I did the exact same thing. It came down very quickly, no smoke, no flame, nothing. What's really interesting about this, and the automotive manufacturers are fascinated about this as well. So again, if you look at the voltage trace, when the nail pen goes in, you see a puncture, which for a short second means we had an internal short, but you can see it recovers. And then the voltage decays, which it should, but it doesn't drop off the table like you would expect from a traditional cell. And the reason why that's important is from a functional safety standpoint. You can imagine if you have some sort of event on the road, it gives the driver time to get to someplace safe instead of just having an event on the highway. So this actually has quite a bit of value in it as well, and we're continuing to explore it. Cycle life has also gotten a lot better. So again, these are on our production intent cells. We should be at about 500 cycles. Again, this is at room temperature to 80% capacity, and we're projecting to get over 1,400 to 60%. This is a substantial improvement from where we were last summer. And then again, we started testing at higher temperature. The rate performance is actually much better here, but we have this same issue that was shown earlier. I think you were pointing this out, that as you go to higher temperatures, we have these side reactions that can happen that can help degrade it. So we're seeing the same thing here, and we think it has to do with actual stability of the ionic conductor in these systems. This is actually really interesting as well. And so what you're looking at is the area-specific impedance versus the state of charge of these cells. And so the fact we actually can get a response at 0 degrees C with a solid-state cell is actually quite unique. And then as you would expect, as the temperature increases, the impedance reduces. And so just to kind of give everybody an idea, this is where you would typically see an 811 cell, just maybe below the 45-degree line. So there's about a 20 to 25 degree C offset in terms of power, and we're working to minimize that gap. So I think I went a few minutes over, so I apologize for that. But in summary, just like in academia or in national labs, a fundamental approach to solving problems is just as important for companies like A123. We've demonstrated that for our next generation, our ultraphosphate LFP, and it's really paid a lot of dividends for us. We're making a lot of progress in the high nickel NMCs. This is an area of tremendous research at A123 currently, and it's helping us really show value to automotive makers like Volkswagen Group, Volvo, Geely, that we're catching up from an energy density standpoint, but also imparting the safety that's required to put these systems on the road. We think solid-state batteries are the future, and it's key to getting to higher energy densities. We're of the same opinion that it's probably a 2028, 2030 for lithium metal for solid states, but if we can get to between 300 and 350 with a graphite silicon and 80 or 85% nickel, there's value there. There's a market for that as well, and we think we can break into that about 3 or 4 years earlier when compared to lithium metal. And I can't highlight this enough. The automotive market for lithium-ion batteries is extremely dynamic. It's fast-paced. It's exciting. There's a lot of technical hurdles to overcome, and for me, it's been a great joy for me to work in it. So thank you for your attention, and if there's any questions,
Any questions for them?
I have like 2 questions. So the first is if you could sort of give us a definition of what you mean by solid state. So is the cathode soaked in a liquid? Is it completely dry?
So it's completely dry. So in this particular case, there's 2 approaches. So there's a polymer ionic conductor that we mix in with in a slurry. It's a binding material that we mix into the slurry, and it has other things in it as well, both on the cathode and on the anode. Yeah. Okay.
So the second question is, so we hear a lot about, what Elon Musk is predicting
Mm-hmm.
for the cost of NCM-based chemistry. But I assume LFP chemistry is even lower. So where are you in terms of dollars per kilowatt hour?
So that's a great question. The low voltage systems, it's difficult because the energy densities there are quite low. So the 48, because it's very power focused. So to give you an example, on the 48 volt system, the energy density is only 80 to 90 kilowatt hours per gram. I mean per kilogram. I'm sorry, 1 hours per kilogram. The higher energy densities that you can only achieve through NMC is obviously much higher. We're at 260. I'm trying to think of where, I'm thinking in RMB right now because that's where our market is. So we're at 0.8 RMB per watt hour. So I think that translates to, I think, $105 per kilowatt hour at the cell level. The problem is if you look at the request from the automotive for launches in 2022 or 2023 for these systems, they're looking for $80 per kilowatt hour at the module level. So it's not just the cell, but all the packaging and electronics that go to the module level as well. And I really think that's going to be a real challenge. Yeah.
I seem to, my impression was that the company has it has very few products currently on the market. And yet you have thousands of employees. I mean, can you explain me what the thing is like?
Interesting.
How do you balance why do you need so many people?
And okay, so okay, appreciate the question. So yes, that's true. We have about 2,500 employees. It varies a little bit depending on manufacturing and the demand. But to give you an idea, so right now our Hangzhou facility is producing about 3 gigawatt hours. So it's almost 3 times what the output of the gigafactory for Tesla is, and that services cell production globally, actually, because we pretty much shut down the Michigan plant because there's just not a market here right now in the U.S. And I think this year for the 48 volt systems we're going to produce 14 million cells. So I'm telling you these numbers because that's why we need the 2,500 employees, because the output from the China plant and the number of cells is actually quite large. So we might not have a lot of products. I think right now we have 7 or 8 cells on the market, but there is a lot of demand for the starter battery and the 48 volt system, and so we need to make the cells somewhere. Yeah.
What is the anode in your 12 volt and 48 volt system?
It's graphite, believe it or not, and
It's not LTO.
it's not. So we looked at that. That's a great question because the issue that you can typically have is for these very high rate applications, especially for 48 volt, it's very charged. It's the charge acceptance has to be very good, right? And so you need very, very low DCR on the charge side. And the worry is that if you had a graphite anode, especially starting to middle to end of life, when the impedance increased, you would start plating lithium and you'd get rollover on the performance. But between the design of the actual electrodes in terms of loadings, again, that's why one of the reasons why the energy density is so low, and porosity, and the fact that we can reduce the overall impedance in the system because of the advantages or the innovations on the LFP side, we're not seeing the lithium plating. But that was a question that was up in the air in our mind about when I started 4 years ago, is do we need to go to an anode that had a charge voltage that was higher than what graphite is, so that when you do it in a charge situation, we don't have an over potential and plate lithium on the anode. Yeah.
I want to go back to the question of solid-state batteries.
Okay.
You told me you put some kind of mixture and so on.
Yes.
Do you have a what? Solid-state or polymer battery?
It's polymer.
Okay. Second question. Now, do you have any liquids?
No.
If I pump a new battery, I don't have any liquids coming out.
No liquids coming out.
Not sure this stuff. Not sure this stuff. Okay.
Yeah. So that, I mean, it's always a good question, right? Because
No, it's not a good question. It's a real question.
yeah.
Because you need to advise. And the second joke.
No, it's an important one because in this particular case, what we've been able to do is a process that mitigates the contact resistance in the layers in and of itself on the active material and the polymer. And the polymer, we don't do any of the material that's all from Ionic Materials, and they've done a great job.
Okay.
So that's that. I do not have we don't have the internal expertise of that. So everything that we've shown had the ionic conductor and the polymer from Ionic Materials. Yeah.
Which one?
It's good. Any other questions? Okay, if not, let's thank the director.
Thank you.
We'd like to thank all the speakers and your attending this symposium. But we have one more thing. There will be a poster session the other side of this building, near the cafeteria. There will be posters. Take a look at some of the posters.
Thank you. Thank you. I appreciate it. Again, thank you for the invitation.
We have a lot of progress in solar systems.
It is, and so for us, I mean, Jean-Marie's question was a good one. So we made the decision early on